2-3 proofs for you, the induction part. So our claim is that for a tree with n greater than or equal to 2 vertices, that the number of leaves is this expression. So remember, leaves are just vertices whose degree is equal to 1. So let's give ourselves some notation and refer to the number of leaves as L. So we want to prove that L is equal to 2 plus the sum of the degrees of the vertices minus 2, where we sum over all the vertices whose degree is greater than or equal to 3. Like we mentioned in the previous problem, whenever we're doing graph induction, we normally want to prove that some property A implies some property B. So let's start off with our base case. So our base case, since n has to be greater than or equal to 2, is going to be on n equal to 2. There's only one tree with 2 vertices, and it looks like this. So now let's just count the number of leaves and see that it matches the summation. Well, both of these are leaves since both of them have degree 1. And since there are no vertices of degree greater than or equal to 3, this whole summation is equal to 0. So the number of leaves is indeed equal to 2, and the base case checks out. Let's move on to the induction hypothesis. So for our induction hypothesis, let's set k greater than or equal to 2, and assume that property A implies property B for all of the graphs of size less than or equal to k. In our induction step, we want to show that this also holds for k plus 1. In other words, we want to show that property A implies property B for graphs of size k plus 1. So to do this, following the steps from the previous problem, we're going to start off by considering an arbitrary graph with k plus 1 vertices that satisfies property A. Let's call our graph T because it's going to be a tree. So T might look something like this. Starting from this graph, we now need to modify it to get to a smaller graph. Well, since this is a tree with k plus 1 vertices, we know it is guaranteed to contain at least one leaf. Let's call this leaf W. Since W has degree 1, it is connected to exactly one other vertex. Let's call this S. A really nice way that we can get from a bigger tree to a smaller tree is just by cutting out this leaf. So if we cut out this leaf W, the remaining part is going to be our smaller graph T prime. For the notation of this proof going forward, I'm going to refer to all the vertices in T by a letter, and when they're inside of T prime, I'm going to prime them. So we call this S when we're referring to S within the overall graph T, and we'll call it S prime when we're referring to how it is within the smaller graph T prime. Going forward with our proof, we want to cite the induction hypothesis on T prime. In order to do that, we need to show that T prime satisfies property A. So property A is that T prime has to be a tree, and it has to have greater than or equal to 2 vertices. Well, we know that T was a tree, and all we did is remove a leaf. Well, removing a leaf doesn't disconnect the graph since it was just a leaf, and it doesn't add any cycles since we're removing vertices. So indeed, T prime is a tree. Does it have greater than or equal to 2 vertices? Well, T had k plus 1 vertices, and we removed exactly one vertex, so T prime has k vertices, which is greater than or equal to 2. Thus, T prime satisfies property A. With that out of the way, we can go ahead and cite the induction hypothesis on T prime, and say that it satisfies property B as well. What does it mean for T prime to satisfy property B? This just means that the number of leaves in T prime, let's refer to this as L prime, is equal to this expression. Our goal is we want to show that T also satisfies property B. So we want to show that the number of leaves in T, L, is equal to this expression. Note that the only difference between these two is what we're summing over. This summation goes over all the vertices V prime inside of T prime, while this one goes over all the vertices V in the overall T. So what's really the difference between T and T prime? Only 2 vertices were affected when we did this removal. W because it ceased to exist, and S because it lost one of its neighbors. So how does this affect the number of leaves? We know that this property holds for the leaves in T prime. What changed between T and T prime in terms of the number of leaves? Since only S and W were affected by this modification, we can really case on whether or not S became a leaf. So we can split this up into 2 cases. When we did this removal of W, either S became a leaf or it did not become a leaf. In the case where S became a leaf, this just means that the degree in S at the very start in the overall graph T was equal to 2, and then when we removed its neighbor W, its degree became 1 and it turned into a leaf. Visually, that means the graph looked something like this, where S was connected to W and one other thing. We know S is connected to W by definition, and since its degree is 2, it was only connected to one other thing. After we removed W, the graph looked something like this, so the degree of S prime was equal to 1. Note what just happened. We lost a leaf in W, but S became a leaf, so we gained a leaf back. So overall, the number of leaves doesn't change. L is equal to L prime. So we can just plug in what we know for L prime and say that's what L is. Looking closer to what we want to show. The last question is, can we just change all of these V primes and turn them into V's? Turns out, yes, we can. Because as we're doing the summation, when we were summing over all of the V primes, we were actually summing over the exact same vertices when we're summing over the V's from T. This is because the only two vertices that were affected, S and W, aren't included in the summation. This is because W, being a leaf, has degree 1, and S, in this case, has degree equal to 2, so neither of them show up in the summation. So it doesn't matter whether we sum over the vertices in T' or T, it'll be the same summation. So this case checks out. The second case is when S does not become a leaf. This means the degree of S must have been greater than or equal to 3, looking something like this. We know by definition S is connected to W, and it must have been connected to at least 2 other vertices. After we remove W, the degree of S goes down by 1, and it looks something like this. This means we lost a leaf when we lost W, and we didn't gain a leaf because S didn't become a leaf. So the number of leaves went down by 1, so L is equal to L prime plus 1. Plugging in what we know for L prime, we would get this plus 1. Once again, we would like to convert this summation, so instead of V prime, it has V's instead. But this time we can't just switch it because we feel like it. We have to compensate for the change we made. Originally, when we were at V prime, S prime was included in the summation. Now that we changed from V prime to V, instead of S prime, we're counting the degree of S. To compensate for this change, we need to add back in the degree of S prime minus 2 that we lost, and subtract back out the degree of S minus 2 that we added in. From here, let's try and simplify what we've got. For starters, this minus 2 can cancel out with this plus 2. Then we can go ahead and plug in for degree of S prime what we know the relationship between the degree of S and the degree of S prime. Plugging this in, we would cancel out the degree of S with this degree of S, and we would cancel out this minus 1 with this plus 1. So after plugging it in and doing all that algebra and simplification, all of this stuff cancels out, and we're left with exactly what we wanted to show, that L is equal to this expression. And we're done! To see this proof done again using a degree counting argument instead, check out the next video.